Yeah. All right. Hello, everyone. Today I will present about my experience with a technique for performing well-found recursion. I did this in a project with my supervisor, Herman Geuvers, who is not here today. I did this project because 2 years ago at the same conference, Xavier Leroy presented a technique for performing well-founded recursion. As you know, in Rocq, all functions must terminate. And this can often be verified syntactically if you only recur on structural subterms. But not all functions are structurally recursive. So one example is quicksort. Very briefly, quicksort, it takes a list and sort it by taking the head as the pivot and then partitioning the tail into those elements that are smaller than pivot and those elements that are greater than pivot, recurring on those two parts and concatenating them. But these sublists less and more are not structural subterms of the list L, and so this definition like this is rejected. And hence we must use well-found recursion in this case. There are multiple ways you could go about this. There exist various plugins like functions and most notably equations. But in this talk I will look at Leroy's method from 2 years ago, which is more a manual. I think it's an instructive technique, and so that's why I like to present it. There's two parts to it. First, we're going to define the function and then prove a property about it, and I'll show some practical tips, and this is really a pragmatic guide, you could say. And we'll use quicksort as our running example. So, part one. First, let's briefly recall well-foundedness. So a relation is said to be well-founded if all its elements are accessible under that relation. And accessibility here is defined inductively. So an element is accessible if all R predecessors, where R is the relation, are also accessible. And this is equivalent to saying that there is no infinite descending chains, which intuitively means you can perform induction on this relation because you eventually always reach a base case. And well-founded reduction is, well-founded induction is essentially equivalent to performing structural induction on this proof of accessibility, and you can use the same idea to define recursive functions. So let's go back to our example on quicksort, and we'll start with the naive definition, which, like I said before, is not accepted because less and more are not structural subterms. First, we must determine, of course, why at all this function terminates. It's not that hard to see, because less and more, in this case, never contain the pivot x, so they are strictly smaller. So more precisely, if you would compare these lists by their length, then they would strictly decrease every recursive call. And that's why we'll define the relation on our lists as follows. We compare them by length. Next, this is really the crucial step. We add an auxiliary argument here, which is the proof of accessibility of the list L under the relation R. And then in the recursive calls, we must also provide terms for this, of course, and they must be subterms because eventually we want this definition to be structurally recursive in Rocq. Leroy suggests to use the inversion lemma Rocq-inv for this, and since Rocq is inductively defined, so you can essentially extract the accessibility of smaller elements, and you only need to give a proof here in these holes of the fact that less is indeed smaller than our argument L. And so there's two holes here. There's multiple ways to deal with this. You can provide exact proof terms, but then you know exactly, you need to know exactly what you need to put in. So it's easier to generate obligations for this. You can use a refine, but I think program works most nicely. And then, yeah, I mean, it's a trivial remark, but the obligations are defined, so you can clearly see what you need to prove, and this really allows you to follow these steps quite mechanically. In this case, they're very similar, so we can capture them with one lemma here. you can prove it, and then a really nice trick, I think, is to add this lemma to a hints database. Here I'll just add it to core because it's easy. And then our previous definition will be accepted because it tries automation. And this will also be convenient because later we can use this again. And now a nice observation is that this definition is accepted and it is structurally recursive now in the proof of accessibility. We're not done yet, however, because, well, quicksort is a function from a list to a list, and it should not take this accessibility argument, so we need to eliminate it. And this means that we need to provide for every list a proof of accessibility, and this is exactly the definition of well-foundedness. So our last step will be to prove the well-foundedness of our relation and supply it to our function. You can prove well-foundedness from scratch, but it's kind of annoying and tedious. So it's easier, I think, to essentially lift it from the well-foundedness from another known relation. And there's a nice theorem in the standard library called the WF inverse image, which essentially says that if relation S is well-founded, then a relation which compares two elements x, y via S under the image of some function f, then this relation is also well-founded. And in this case, f would be length and S would be the less than relation on natural numbers. And actually this case, I guess, occurs so often that there is a specialization in standard library as well, which is precisely substitutes the less than relation for S. So that's what we'll use here. We have in one line, we have the well-foundedness of our relation, and then we can fill it in, and we have a nice, clean definition of quicksort, which is accepted. So, of course, the next step would be to do something useful with this. So we're going to try to prove a property, and in fact, it's very easy to do so. There's only one catch, I guess. You have to be a bit careful. As I said before, this definition is structurally recursive in Rocq, so it might feel tempting to perform induction on Rocq. Well, there's some dependent typing going on, so you run into issues, and this is not really recommended. So instead, you can perform well-founded induction on the original decreasing argument, L. And that is what we'll do here. So first, very simply, state the lemma you would like to prove. In this case, the sorted list contains exactly the same elements as the original list. This is, of course, is not valid because Rocq is missing, so we add it. A small detail here. In the proof, eventually, or in the proof, you would like the induction hypothesis to be general over the accessibility, so it's easiest to add it last in the quantification. Then we start the proof by well-founded induction. This gives us the induction principle, and we need to, again, give the well-foundedness we showed before. And we can unroll the function by destructing the accessibility, and now we can continue as usual. At some point, you will, of course, apply the induction hypothesis, and then the goal, most likely, is exactly an obligation as you showed during the definition, because you need to show that the argument you apply the induction hypothesis on is smaller than L, basically. So this is exactly an obligation. And because we added them previously as hints, this lemma, the goal can be just discharged immediately. And so this is a small bit of convenient automation. So we defined a well-founded recursive function using only basic elements, really, without relying on fancy plugins like equations or function. And I would say there's also quite a straightforward design pattern for this. You can follow these steps I laid out. And I especially like adding these obligations as hints and deriving the well-foundedness using a theorem from the standard library. I also made kind of an introductory tutorial for students, and it's available here. And I applied this method on another algorithm on trees with a more specialized relation. So for another example, if you're interested. The method does introduce some boilerplate in the definition because you need to add these accessibility arguments, but I think it's still quite legible. Also, a nice property of this method is that the extraction is really clean because this accessibility argument is in prop, so it disappears completely, and you're basically left with a very clean extraction to OCaml or whatever you like. Another thing I really like about this method is that basically you see everything that's going on. With other methods like equations, there are automatically maybe some wrappers or tupling is happening secretly in the background. You're not really sure, or I am not really sure as a user. But here, really, every step is clear. And I think that's especially useful for students like myself. It's a really good way to learn about well-founded recursion, I think. So, thank you.
Questions?
Hey guys, not so much a question, but just to remind you, on the Rocq website now there's a page dedicated to tutorials and stuff like that. So if you write a tutorial like this that you think can be useful to a bunch of people, just write a small pull request, we'll merge it, and then it will be on the website updated with the Rocq version, and it will give it more visibility. So don't hesitate doing it.
Want to do something mutually inductive?
That's a great question. That's something I did not look at yet, but that would be interesting future work for sure.
Yeah, thanks for the nice demo. So, if I understood correctly, what happens here, what you mentioned at the end with this auto thing, is that the actual termination argument of like the length is getting smaller, you're kind of reproving this when you're doing the proof. Right, like this auto here redoes the proof that the length is actually decreasing.
Yeah, it basically uses the QS obligation lemma that I defined before.
Right. Which seems a bit odd because we already proved that things are decreasing when we wrote the function. Which, I mean, in your case, so you automated it, so it's fine, right? But in general, maybe this argument is complicated or something. Like it's from a principled perspective, it feels a bit odd that I have to redo that proof. Do you think there's any nice way to avoid that?
I'm not sure because if you perform induction like this, it will be part of the induction hypothesis, and so this, like this, I don't think it's can be avoided.
When you do structural induction, I don't know when you do structural induction. I mean, basic structural induction in Rocq. If you define your functions, your fixed points structurally inductively, and then you prove your lemmas structurally inductively. It's not like you can follow.
Yeah, I don't think that's an So my understanding is that if you were to do an induction on hack, then you would get this obligation for free. But since you're doing a separate induction and then a destruct, the destruct gives you the wrong thing, and so you still have to prove the right thing. But it's very easy in both cases. And as you said, the induction on hack doesn't work very well because it's dependent induction, and then everything goes wrong.
This is more a question from Xavier. Would doing inversion of hack allow to get the correct? Would it allow to get the correct term and not have to redo the proof?
If you manage to do dependent I guess the question is, if you can do dependent induction nicely in code, then yes, probably. But it's beyond my abilities of using Rocq.
we need to move forward, but during the break you can still discuss this.